Have you done something here? Put the sheet here. Okay, so I just put up this for reference. If you remember, we had a 2 Tangson series, and we solved this a number of times. First, we solved it with, that's on? Is it recording?
Yeah.
First, we solved it with method of ordinary differential equations, and then we solved it with Laplace transforms. So here I'm just reminding you what the Laplace transform of CA1 prime and CA2 prime are. CA1 prime tilde, CA2 prime tilde, and depending on how far we get today, I may refer to those later or I may not if I don't get to it. But I wanted to have them on the blackboard just in case I did. And now, at the end of the last hour, we were talking about inverting Laplace transforms. So clearly here we were left with Laplace transform 1 over 1 plus st. It was 1 over 1 plus st1, 1 plus st2. If t1 and t2 are the same, that is if both reactors are the same size, then this would be 1 over 1 plus st squared. Now it just happens that both of those are in the table. But we would like to consider the situations where, for example, let's say I have 3 reactors in series. What do I do in that case? That one's not in the table. So then I would have 3 factors like this. So, and again, what we're interested in general is, naturally, is the behavior in the time domain, not the S domain. But it turns out that the S domain gives us a way with much less algebra of solving these problems, much less algebra than the method of ordinary differential equations. And as we'll see as we go on, it also has many other advantages. So we noted that there were 3 cases. There were 3 cases to deal with. One of the cases that we would consider. So one case was where, so let's say we have some quantity, a numerator or a denominator that we need to invert. So for example here, numerator is a constant, denominator is this. Numerator, denominator. We could have more complicated cases where the numerator also is a function of s. And we're going to look at the situation where n for numerator, d for denominator, are each polynomials. So if they're each polynomials, and I'm going to assume that I've canceled all like factors, because I can always factor a polynomial into I can always factor it into s minus alpha 1, s minus alpha 2, etc. And I assume that I've canceled the like factors. So, and I'm also assuming in case 1 that all the roots of d tilde are distinct, that there are no repeated roots. Case 2, I will allow repeated roots. So I actually solved this last time, but I just want to review it. So for case 1, we said if we look at a particular root, say alpha, we could write n tilde over d tilde as m tilde of s over s minus alpha. That is, I take the one root from d tilde out, and everything else I lump into m. And what we saw is that we could figure out what m tilde over s minus alpha can be written as a constant over s minus alpha plus the rest. And I did an example. And we figured out that C1 is just m tilde evaluated at alpha. And it could also be written as the numerator evaluated at alpha over the derivative of the denominator evaluated at alpha. And we note that the derivative of the denominator is often easier to take, that derivative, than it is to actually, we can note that it's typically easier to take the derivative and use this for calculations than it is to just write the whole m tilde of s out. But it doesn't matter. You can also just write it as m tilde of alpha if you prefer. And therefore, and then r tilde of s has the rest of the roots of d tilde n. So if we write it out, if we just keep repeating this, we find that n tilde over d tilde is the sum of coefficients times 1 over s minus alpha I, where I sum over all the roots. And if I have something more complicated, if it's not just a polynomial, then I may still have something left. If it could be polynomial times something, say a sine or a cosine or whatever. But right now, I'm not really worried about this. And we showed how to actually calculate r tilde last time in an example. So now, it's easy to get lost in the math. So the question is, why am I fussing with all this? Because when I do the inverse, what we saw was that we could write 1 over s minus alpha, 1 over s minus alpha, we could write it this way as 1 over minus alpha divided by 1 plus s over minus alpha. So this is exactly in the form, in the table of a line 4. Line 4 is 1 over 1 plus s tau, where tau is playing the role of 1 over minus alpha. So then when I do the inverse, according to line 4, I find that the inverse of 1 over s minus alpha I is just e to the alpha t, in which case the solution is just a sum of coefficients, which we know what they are, times times e to the alpha I t plus the inverse of r tilde, if I need that. But I'm not worried about that right now. And what we noted last time is that's what's really important here. Typically in most problems we're interested in, does it reach a steady state or does it not reach a steady state? And if it does, what is that steady state? Well, if the alpha i's are all negative, then all the exponentials go to 0 at long time, and it reaches a constant. The constant may come from here, for example. If say one of the alpha i's is 0, let's say one of the alpha i's is 0, then that particular term in the sum, the exponential is 0, and I just have a constant here. And that could be the steady state value. On the other hand, if even one of the alpha i's is positive, then the exponential blows up, and then I don't reach a steady state. So that's why this is important. Any questions on that before we go on to new stuff? Okay, so the next case is case 2. Now, I'm sorry I wrote this on this blackboard. That means I'm going to need access to this blackboard anyway. So I would advise not to sit directly next to that blackboard because I'm going to be writing on that blackboard.
Can you take the limits before you go back and cross out some terms?
I'm sorry, I don't understand.
What is in the S space?
I'm in the S space.
Can you take the limit there to cross out those exponential terms, and then, because to get the steady state value, you'll have to go back to the time domain, right?
Yes.
So can you cross out values before you go to the time domain, or?
Which limit are you talking about? Because the limit is at t goes to infinity. So when I'm in the S domain, I can't really go t goes to infinity because it's not a function of t. What I could use is the final value theorem. So that in the S domain. So I can certainly do that.
Okay.
Yes, so I can certainly do that, but I can't take a more general limit in the S of t when I'm in the S domain. I can only look at t goes to 0 and t goes to infinity, which we proved corresponds to an S limit of S goes to infinity or S goes to 0. So those things, so I can certainly do that. I can use the final value theorem. And what you'll find in the final value theorem is if one of these is positive, then the final value theorem will also give you an infinite value, an infinite solution, an infinite value.
Thank you.
Sure. Any other questions? Okay, so don't forget to sign the attendance sheet, was right on this table. Please put it back there. That's why I have the back there. So case 2 is a case where I have multiple roots. What does multiple roots mean? That would be the case, for example, where t1 equals to t2. So I have 1 plus st quantity squared. So the root is minus 1 over t, and it's there twice. Now, why is that interesting? Well, if you look at, for example, the table in line 6, we find that 1 over 1 plus s tau to the n, the inverse, gives me 1 over tau to the n, t to the n minus 1, e to the minus t over tau over n minus 1 factorial. So now we can, because we know this, we know that tau plays, minus 1 over alpha plays the role of tau, so we can see that 1 over s minus alpha to the n, the inverse of that, well, we have a t to the n minus 1, and now e to the minus t over tau. Tau is minus 1 over alpha, so that's e to the alpha t over n minus 1 factorial. And notice that when I take this to the nth power, I have a minus, I've got a 1 over minus alpha to the n, because I'm taking it to the nth power. And then I also have 1 over tau to the n here. Tau is minus 1 over alpha, so it's 1 over minus alpha to the n. These cancel, and I'm just left with the square bracket. So if I learn something about this, then I know how to invert that here, directly from it. So let's see how I go about doing these types of inversions. So let's say, so again, this is case 2 continued. Continued. So let's say I have n tilde over d tilde. And let's say that's equal to m tilde of s over s minus alpha to the n. And actually, let's make it n plus 1. Just makes, it happens to make the notation a little bit nicer. I claim that that's equal to c1 over s minus alpha plus c2 over s minus alpha squared plus dot 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 plus cn, right? Or cn plus 1. cn plus 1 over s minus alpha to the n plus 1 plus r tilde, right? Yes, plus r tilde. Now you might say, wow, that's complicated. This one only gave me a c1 over s minus alpha. But remember, m tilde is a function, and here we're replacing the function by a constant, plus whatever's left. So this is a big deal, this simplification. And then we had to calculate what c1 was. Well, over here we're replacing m tilde. See, we don't only just have 1 over s minus alpha to the n plus 1, we also have m tilde in the numerator. And it gives me a whole bunch of constants that I have to determine, plus whatever's left over. So just as we did here, where we determined what C1 was, now we have to determine what C1, C2, dot, dot, C, n plus 1 are. Everyone sees the problem? Okay, how many do we have here today? 2, 4, 6, 8, 10, 12, 14. So 5 people still didn't get the message and have to come to class. All right, well, let's multiply both sides. Multiply by s minus alpha to the n plus 1. If I do that, then I have m tilde of s is equal to c1 s minus alpha to the n plus c2 s minus alpha to the n minus 1 plus dot 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 plus cn s, let's see, cn, so s minus alpha to the n plus 1, yeah. S minus alpha plus Cn plus 1 times 1 plus R tilde of S minus alpha to the n plus 1. So all I did is I multiplied out by S minus alpha to the n plus 1. And now I'm going to let, now I'm going to take M tilde of alpha. If I take M tilde of alpha, this is 0, this is 0, this is 0, and this is 0. The only thing left is Cn plus 1. Is that clear? Now, okay, that's great. I got Cn plus 1, and I got a bunch of others. So let's take the m tilde of s ds. What happens when I do that? Then I get C1 n s minus alpha to the n minus 1 plus C2 s minus, n minus 1 s minus alpha to the n minus 2 plus dot 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 plus Cn, I kill that, and this is 0, and here I have plus R prime tilde of s, s minus alpha to the n plus 1 plus R tilde of s minus alpha to the n times n plus 1. So now I've isolated Cn. So I can note that dm tilde ds at alpha n, at alpha, is just equal to Cn. Because all these other guys have factors of s minus alpha in them. So when I set equal to alpha, that's 0. How about the next one? d squared m tilde ds squared. That's C1n, n minus 1, s minus alpha to the n minus 2, plus C2 n minus 1, n minus 2, s minus alpha to the n minus 3, plus dot dot dot, plus Cn minus 1, that's going to be the 1. Now, what happened with, remember, Cn minus 1 had, let's just remember, Cn minus 1 had s minus alpha squared. So when I take a derivative of that, I had 2Cn minus 1 s minus alpha, and now I have 2Cn minus 1. when I take the second derivative of that, plus the stuff involving the R tilde, plus the R tilde stuff. That has lots of powers of S minus alpha. So when I set this at S is equal to alpha, this cancels, these cancel. The only thing left is 2Cn minus 1. So I have d squared m tilde ds squared at S equals alpha is equal to 2Cn minus 1. And what you can see here is that when I take one derivative, I just got a 1 coming down. I took two derivatives, I got a 2 coming down, and then a 1 coming down in the second derivative. If I take 3 derivatives, that'll give me the Cn minus 2, which will originally be multiplied by S minus alpha cubed. So the first derivative will have a 3 coming down, the second derivative will have a 2 coming down, the third derivative will have a 1 coming down. So you can notice I'm going to get an n factorial. And what you find is that d to the j m tilde over ds to the j at S equals alpha is equal to j factorial Cn minus n minus j plus 1. And now how did I get that? Well, remember when I take two derivatives, I just have n minus 1 because I started at n plus 1. So it's n plus 1 minus j. Maybe I should write it that way. I started at n plus 1. So when I take j derivatives, I knock down j of them. So immediately, so if I rewrite this, I have Cn plus 1 minus j is equal to the jth derivative, which I'll write this way as, evaluated alpha over j factorial. So now I know what each of the coefficients is. It's this. And I know what the inverse of S minus alpha to a power is. The inverse of S minus alpha to a power is just this. 1 over S minus alpha to the j is just t to the j minus 1 e to the alpha t over j minus 1 factorial. So I can put it all together, and I can note that if I call this f tilde of S is this, then f of t is equal to, it's a sum of terms. So here it's a sum of terms, which I call sum on j, for example. And it starts from 1 and goes to n plus 1. Starts at 1 and goes to n plus 1. And then I've got the coefficient, before I get the coefficient, I've got 1 over s to the alpha minus alpha to a power. So I've got 1 over s minus alpha to the j. So that inverse gives me a t to the j minus 1 e to the alpha jt over j minus 1 factorial times the coefficients. Now the coefficients, I don't want n plus 1 minus j. Let's call this j prime. I don't want Cn plus 1 minus j prime, I want Cj. I want Cj. So if j equals n plus 1 minus j prime, well, that's okay. So then wherever I see a j, so I always want the n plus 1 minus j prime. Or the other way around, yeah, so I want a Cj. Okay, so that tells me this is m. So I don't want Cn plus 1 minus j prime, I want Cj. So the subscript I want to be equal to j. So wherever I want a j, I have to plug in an n plus 1 minus j prime. So this is n plus 1 minus j factorial, because instead of j prime, I now have n plus 1 minus j. And here I have an m tilde, and which derivative? It's n plus 1 minus j. And of course, here I have the inverse, r tilde of s, inverse, whatever that is. Okay, now the algebra looks complicated, but it's really just algebra. It's keeping track of subscripts and notation. Now, this is a little bit beyond, above and beyond, for those of you who are interested in a little bit of math. You could also note that this is equal to, you can notice something. Notice that the number of derivatives of m plus the power of t, if I add them together, the j's cancel, the 1 cancels, and I get an n. They always add up to n. So no matter what j is, those two always add up to n. So you can notice, and again, this is not trivial. It's 1 over n factorial times d ds to the n of m tilde of s times t to the e to the st, evaluated at s is equal to alpha. Now, where did that come from? So I don't want to spend too much time on that, but has anyone ever heard of Pascal's triangle? Okay, so if you start taking derivatives, so a little aside here. Take the first, if you have m tilde e to the st, and you take the derivative of that. The first derivative is going to be m prime times e to the st plus m times t e to the st. So I can factor out the e to the st. That's the first derivative. Notice the number of derivatives and the power of s add up to 2 here. One derivative, 0 powers of t. No derivatives, 1 to the power of t. So they both add up to 1, to the number of derivatives. The second derivative is going to be m tilde double prime plus m tilde prime t times e to the st. And then I've got the derivative of this with respect to s. So that's just going to give me a t coming down times each of these guys. So it's going to give me a 2 here, and it's going to give me a t squared m tilde here. So notice again, there are 2 derivatives and no powers of t, 1 and 1, 2 and 0. So they always add up to 2, the number of derivatives. And notice the coefficient, and if I do one more, again, this is a little above and beyond. I would have m triple prime tilde plus the derivative of this guy, so I've got 2 m tilde double prime t. Remember, I'm taking derivatives with respect to s. And then here I have a t squared m tilde prime. So that's the derivative of this guy times e to the st, plus I need the derivative of this times this, which gives me an s. So I've got an s m double prime t, that gives me a 3 here. I get another t here, so I get a t squared m tilde prime. T squared m tilde prime, I get a second one of those. I'm sorry, one more of those. I had 2, so now I had, okay, so I don't want to go too quickly. Let's do it again. I just want to make sure I get this right. So m double prime plus 2 of these plus t squared m prime. Right, and now I need plus t times each of these. So t times m double prime is going to give me one of these. T times this is going to be 2t squared m prime. And I already have one of them, so that gives me a 3. Plus this guy times a t plus t cubed m tilde. So that's about as far as I want to go here. Again, the sum of the number of derivatives and the power of t always add up to 3. And if I keep going, another derivative will give me 4. And you can notice what the coefficients are here. So if I start in the top row, the coefficients of these terms are 1 and 1. coefficients of the next terms are 1, 2, 1. And the coefficients of the next one are 1, 3, 3, 1 of the 3 terms. And this is known as Pascal's triangle. Because notice we start with the 1, 1, then every number below adds the number to its left and to its right. So there's nothing to the left, so 1 plus 0 is 1. 1 plus 1 is 2, and 1 plus 0 is 1. And then here, 3 is 1 plus 2, 3 is 1 plus 2, 1 is 1 plus 0, etc. So the next term is just going to be 1, 4, 6, 4, 1, etc. when I take the fourth one. And then I just march down, so I know exactly what those are. So if you notice, the fact that the number of derivatives in each term, the number of derivatives and the number of powers of t add up to n is exactly what we said here. That we have the exponential on the outside, evaluated alphas here, and the fact that these coefficients actually give you these factorials is something that requires a lot more algebra, so I'm not going to do that. But I just wanted to give you a sense of where this comes from. Again, this little bit with the nth derivative is not required. This is above and beyond for those who are just interested in the math. And I'm assuming, since we're engineers, that people are interested occasionally in math. Questions?
Professor, for the f of t equals to some dash box, why don't you use the j prime as you mentioned earlier?
I eliminated j prime.
Okay.
I said j, that is, this is cn plus 1 minus j prime. But I don't want cn plus 1 minus j prime, I want cj. I don't want this guy, I want cj over s minus alpha to the j. So I have to set j equal to n plus 1 minus j prime. And so that's where I got this. I called it j prime because j here is different, is the power of s. And over here, it's just notation. Any other questions? Okay, so let's go on to case 3. Case 3 is where the roots are not, where I could have something like n tilde f tilde of s, which is n tilde over d tilde, is equal to n tilde divided by s minus, this is nice, yeah, s minus alpha squared plus omega squared, where alpha and omega are real. Real numbers. So what that, if you factor this, you get n tilde divided by s minus alpha plus I omega times s minus alpha minus I omega. So where did that come from? Well, let's multiply it out. Remember, I is the basis of the imaginary numbers. I squared is equal to minus 1. We already went through that. So let's look what happens. This is, yeah, okay. So here I have s minus alpha in both of them. So s minus alpha times s minus alpha gives me s minus alpha squared. And then, so I've got, you can think of this as s minus alpha plus minus I omega and s minus alpha plus I omega. So a minus b times a plus b. S minus alpha is a, so a minus b times a plus b is a squared minus b squared. So a squared is s minus alpha quantity squared, and b is I omega. So minus b squared. So that's minus omega squared times I squared. I squared is minus 1. Minus a minus gives me omega squared. So we just multiply that out. Is that clear? And of course, we want to write this in the following form. We're going to write it as m1 tilde of s divided by s minus alpha plus I omega plus m2 tilde of s over s plus alpha, S minus alpha minus I omega. Just the way we did here, we wanted to separate out have each term having a separate, having only one root from the denominator. Again, this is new math for you, so I'm trying to go a little more slowly than I normally do. You may not notice that. My inclination will be going faster. But, so let's see what we can say here. Well, now I might have a remainder term, but here I'm taking where it just looks like this. So I'm not going to worry about the remainder right now. I could, of course, have a sum with this after, but I want to concentrate on these two guys. And now I want to prove to you that m1 tilde of s is equal to m2 tilde of s, that those are the same function. But that's not obvious. So we have m1 tilde. So let's look at 1 over s minus z and s minus z bar, where z, to make the notation simpler, let's let z be alpha plus I omega, and z bar, which is called the complex conjugate, just flips the sign of I. So that just makes the notation a little simpler. And I can just have the m tilde here. Well, so if we rewrite this in this notation, we just have m1 tilde of s over s minus z plus m2 tilde of s over s minus z bar. So I just converted this particular equation to this notation. But otherwise I haven't changed anything. Now what I'm going to do is I'm going to multiply by s minus z bar. So I have m tilde of s is equal to m1 tilde of s times s minus z bar, because the s minus z's cancel, plus m2 tilde of s times s minus z, because the s minus z bars cancel. And now I'm going to look at m tilde of z. So I'm going to set s equal to z. If I set s equal to z, then this term is 0. So I just have m1 tilde of s times z minus z bar. But what's z minus z bar? The z minus z bar, the alphas cancel, and I omega minus minus omega is 2 I omega. How about m tilde of z bar? M tilde of z bar. Well, m tilde of z bar, well, for z bar, the z bar is, when s is z bar, this is 0. So I have m2 tilde of s times z bar minus z. So z bar minus z is this guy minus this guy. The alphas cancel, and I have minus I omega is minus 2 I omega. So now I need a little aside before I go to the next step. So here's a little aside. Z1 plus Z2 bar is equal to Z1 bar plus Z2 bar. How do I know that? Well, Z1 plus Z2 bar, Z1 plus Z2 is alpha 1 plus alpha 2 plus I times omega 1 plus omega 2. And when I take the bar of this, I just flip this to a minus sign. And this is just equal to alpha 1 minus I omega 1 plus alpha 2 minus I omega 2. And that's just Z1 bar plus Z2 bar. Again, you don't have to worry about copying down every little thing. It's on the video, and we'll have pictures on the blackboard before we erase. Let's continue with this. Z1, Z2, the product bar. Let's see what that is. Well, Z1, Z2, if I multiply Z1 times Z2, so I've got alpha 1, alpha 2, and then I've got plus I omega 1 times I omega 2, which which is minus omega 1, omega 2. And then I've got plus I times alpha 1 omega 1 plus alpha 2 omega 2. That's just Z1, Z2. So I took this guy, alpha 1 plus I omega 1 times alpha 2 plus I omega 2. And I just got this. Now when I bar it, I get alpha 1, alpha 2 minus omega 1, omega 2 minus I, alpha 1, omega 1 plus alpha 2, omega 2. Now let's compare that with Z1 bar, Z2 bar. Z1 bar, Z2 bar. Z1 bar, Z2 bar is alpha 1 minus I omega 1 times alpha 2 minus I omega 2. Now let's see what that is. Well, that's alpha 1, alpha 2, yeah. That's this guy times this guy. Minus and minus is a plus. I times I is minus omega 1, omega 2. So I get the same thing here. And then I look at the imaginary part. Well, that's minus I times omega 1 alpha 2. Minus I times omega 1. I got it backwards. This is alpha 2, and this is 1. So I've got minus I alpha 2 omega 1 and minus I alpha 1 omega 2. It's plus there. So I get exactly the same thing. So these are equal. So I've just shown that they're equal. So what does that tell me? That tells me if I add two complex numbers and take the complex conjugate, I get the sum. I get the complex conjugate. The complex conjugate of the sum is equal to the sum of the complex conjugates, and the product of the complex conjugate of the product is the product of the complex conjugates. So that tells me if I have any polynomial p of z bar, that just gives me p of z bar. That is, a polynomial of z bar is just the bar of the polynomial. And for homework, I want you to show that if I have the ratio z1 over z2 bar, that's just equal to z1 bar over z2 bar. So that tells me if I have a polynomial, or even a ratio of polynomials of z bar, I can take the bar off of z and put it on the whole expression. So why is that interesting? Because that tells me that I can take the bar off of this and put it on here. So this tells me this is equal to m tilde of z bar. And I want you to notice from here, if I do two bars, z bar bar, I flip the sign of I twice. So this is the same thing as z bar bar. So this tells me that m tilde of z is flipping the sign of I again. So, and of course this should have been of z, and this should have been of z bar. So m tilde of z says I have to just take the bar of this whole thing. And that's just equal to m2 tilde of z, because taking the bar of this guy is the same as taking the bar inside, times 2I omega. And notice this and this are the same. The 2I omega is the same. So that says the function m1 tilde of z is equal to the function m2 tilde of z. Therefore, m1 tilde of z equals m2 tilde of z. That is, they're the same function. Any questions on that? Is that clear? There's a little bit of algebra there. No one step is difficult, but you have to get a little bit used to what a complex conjugate is. And if you think just geometrically, before I go on, what's a complex conjugate? Remember, in the complex plane, we think of the complex numbers as being in the complex plane. So this is the real axis, and this is the imaginary axis. And a number can have an x and a y. We can think of it as a vector, x and y. And there's also an angle here, theta. So I can think of z, which has a magnitude r, z as some magnitude r times, well, I think of it as x plus iy. And x is r cosine theta. And y is I sine theta, r sine theta. Because x is, I project this way, and y I project that way. It's just basic geometry. Okay, so now you notice you get, in complex numbers and complex variables, you get lots of these cosines and sines showing up. And look, I'm sorry I have to introduce all this new math here, but it's just natural to the subject with Laplace transforms. You have to know a little bit of this complex number math. We're not going to prove any big theorems. Although, as an advertisement, it's a really interesting class to take a class in complex variables because it's calculus done with complex numbers, not just with real numbers, and you get results that you didn't often expect. And so it's actually quite an interesting class, and I'm advertising that even though I don't usually teach it. I teach it as a graduate course here, but they have an undergraduate class in the math department. Okay, so before I go any further, I want to stay with the topic of complex variables. And I want to note that sometimes, we know what e to the x is. We always work with e to the x. But now that we have complex variables, what if I have e to the alpha plus I omega? What's that? What does e to an imaginary number mean? So I know what this is, but what does e to the I theta mean? What does that mean? What does that mean with an I in the exponent? So we want the exponential to have certain properties. If you require the exponential, if you want e to the x plus iy, e to the x plus I, you want your definition of e to the z to be such that when z, if z is x plus iy, well, why don't we say it this way? Let's let z equal x plus iy. Then you want that e to the z, when y is 0, to just give you e to the x. That is, I want whatever definition I make to generalize e to the z, it had better reduce to what I'm used to. Otherwise, it's a dumb definition. I also want e to the z to be differentiable everywhere. That is, for any value of z, I want to know how to take the I assume I want to be able to take the derivative, and I also want d dz of e to the z to be equal to e to the z for all z. If you just require these three properties, nothing else, if this is what you require, then the only choice for e to the I theta is cosine theta plus I sine theta. It's the only choice. And if you want to try proving that as extra credit, you can try proving that on your own. You could obviously look it up. But that's the only possibility. And once you have this, it has all the right properties. So for example, from your high school trigonometry class, you can look at e to the I theta 1 times e to the I theta 2 and show that that's equal to e to I theta 1 plus theta 2. And actually that one I'll assign for homework. So show this. It's just high school geometry. That is, cosine plus I sine theta is e to, for this and for this, and you multiply them together and you get this, and you use some trigonometric identities to get there. Okay, so why am I doing that? Well, because I'm going to go over to this board and continue. Do you want to turn the camera? Okay, So I've got M over S minus C. So this is 3 or 2 M tilde over S minus Z plus M tilde over S minus Z bar. And let me just make sure I got that right. So these are empty desks. So this is M tilde of alpha plus I omega, and this is M tilde of alpha minus I omega. Because remember, we're evaluating them somewhere. That's the whole point. And so this is going to be some complex number. Z is, and let's be specific, this is S alpha plus I omega, and this is alpha minus I omega. So, and this is F tilde of S. Okay, so you don't have to take the pictures yet because I'm not erasing. Okay, so this is, and I just want to make sure that, yeah. Okay, so I'm going to let this guy, let's let M tilde of alpha minus I omega, that's some complex number, I'm going to allow that to be A plus IB, where A and B, it's just some complex number. And since this is M tilde of Z bar, M tilde of Z is just the complex conjugate of this. A minus IB. So let's notice I have F tilde of S is equal to A plus IB, and actually let's do of T. A plus IB times the inverse of this guy. Well, remember, the inverse of 1 over S minus alpha is just e to the alpha t. So I've got e to the t and this term is a minus IB. Did I do it right? This is a minus IB. I did it backwards. This is a minus IB. A plus IB is this one, a plus IB. Yeah. Times e to the alpha minus I omega t. So what did I do? I let this guy be a plus IB, and then I had this guy be a plus IB. Did I mix them up? So this is a minus IB times e to the this t, right? And this is a plus IB times this. That's correct.
Should there be a total over the T?
Should there be? There's no total. Thank you. Okay. So let's factor things out here. So I can notice that I've got a times e to the alpha t. A times e to the alpha t. And here I've got another a times e to the alpha t. So the first term with the a's just has an e to the alpha t on the outside. So let's e to the alpha t times, actually with the a here. And what that's multiplied by is e to the I omega t plus e to the minus I omega t. So I've got this guy and this guy comes in. And now I have a b. So now I've got a b, IB, times. So with IB, I've got What's that being multiplied by? That's also being multiplied by e to the alpha t. E to the alpha t. So I could have actually just factored that out altogether. And here I've got, this is e to the minus I omega t. And here I have minus e to the I omega t. And I have a sign I don't like, but we'll fix that later on. E to minus e to the plus I omega t. Did I get this right, or did I screw up the signs? Okay, so this one is a minus ib times e to the alpha plus and let's just see if I got that right. I think I screwed one of them up. So let's go back here. So yeah, so I need m1 of s times s minus z. So I have m1 of s over s minus z. And I think I have them backwards. So m1 of z, m1 of z is m of z over 2i omega. Okay, so I showed that they're the same function. And how am I doing on time? Plenty of time. And I just need to know which one's which, because I think I got them backwards. I want M1 over there. Yes, okay, so I had it backwards. So over here, I have m1 of z, m1 tilde of z is m tilde of z over z minus z bar. So what's over z minus z bar? It's m1 tilde of z over, is m tilde of z over z minus z bar. So when I have the z bar, z minus z bar, I have m1 of z. Not m1 of z bar. So what's backwards is this should have been minus here, and this one should have been plus. So when I do that, that switches the sign. That switches the sign. This should be plus. So let's get the signs right here. So this one is a plus IB times e to the times that a plus IB, that's a plus, and this one should have been a minus. And let's get this right now. Now this is minus, and this is a plus. So let's just go back and see what we did. So if I go back over here, what we showed here was that m1 tilde of z was equal to m2 tilde of z. It's the same function. But how do I know what m1 tilde, what it is? It's the same function, but what is it? So let's figure out what it is. Well, we know what an m1 tilde of z is. m1 tilde of z is m tilde of z divided by z minus z bar. So m1 tilde of z has a z minus z bar in the denominator. So m1 tilde of s is m tilde of s over s minus z bar. So when I have an s minus z bar in the denominator, I have m1 tilde of z in the numerator. So when I have z here, I have z bar here. When I have z bar here, I have z here. Sorry, I messed that up before. Okay, so now if I have both of these guys, now let's go through the algebra again. So alpha, m tilde of alpha minus I omega is a plus ib, so I've got that. The inverse of this is e to the alpha plus I omega t. And this is m tilde of alpha plus I omega, which we say is a minus ib. And that times the exponential e to the alpha minus I omega times t. And now I factor out e to the alpha t from both of these. And here I have a times e to the I omega t plus a times e to the minus I omega t. And I have b times e to the I omega t minus b times e to the minus I omega t. Okay, so let's notice what these guys are. Recall we said, we determined over there that e to the I theta is equal to cosine theta plus I sine theta. And by the way, this formula is known as Euler's formula. Euler. Well, let's look at what happens if I have e to the minus I theta. That means I replace theta by minus theta. What's the cosine of minus theta? What's the cosine of minus theta? Come on, this is really 10th grade. Who passed math in 10th grade?
It's cosine theta.
Cosine theta and the cosine minus theta are the same. What is the sign of minus theta?
Negative sine theta.
Minus sine theta. If you're having trouble with this, I really don't know what to say. This is really high, 10th, not even 12th grade material, 10th grade material. Okay, so if I add these, then I find that cosine of theta is equal to e to the I sine theta, e to the I theta plus e to the minus I theta over 2. Because I get 2 cosine theta, these cancel, is the sum of these. And the sine of theta, if I subtract them, the cosines cancel, and I get e to the I theta minus e to the minus I theta over 2i. This is a direct result of Euler's equation. So notice, this looks almost like a cosine. I just need to divide by 2 and multiply by 2. And this looks just like a sine. I need to divide by 2, multiply by 2, and multiply top and bottom by I. And maybe I should put those extras in a different color since they weren't there originally. Okay, so let's make it orange. I multiplied by 2 and divided by 2. I multiplied by 2 and divided by 2. And I multiplied by I and I divided by I. So now we can look at f of t. And what we find is that f of t is equal to something. F of t is equal to, well, it's equal to e to the alpha t, because that comes out of both. And now I've got 2a, well, I'm going to have a 2 in both, so let's take the 2 out. And let's make this legible for a change. 2 e to the alpha t. And here I've got a times the cosine of theta, where theta now is omega t, plus, well, let's see, is it plus? I've got the 2 I factored out, and the alpha t I factored out. What's left is I squared. What's I squared? Minus 1. So I've got minus b sine theta, sine omega t. So why is this interesting? Well, let's review what we said before. When we were in case 1, it was interesting because the answer were exponentials, either exponential increase or exponential decrease. It either goes down or it grows. Over here, when I had multiple roots, I had a sum of terms, each one of which either grew exponentially or decreased exponentially. But I got a sum of exponentials. Also, no big surprise. They either grew, and because they all have the same, I have to go, because they're all going to, actually I don't need the j here. This is for a particular alpha, for 1 alpha. That's why you don't take pictures till the end. This is for a particular alpha, where that's, where you have a root that's n times, an n root. You've got a sum of terms times an exponential, where the exponential is either growing or decaying. And all this other stuff, well, you have t to a power times an exponential. So the exponential wins over all the t to the powers. The exponential always beats out the powers if alpha is positive. If alpha is positive, everything blows up. If alpha is negative, then if alpha is negative, we know when exponential decays. But if I multiply it by t to the n, then initially it goes up, because when t is small, this is around 1, and this goes up, it starts to grow, but then eventually the exponential kills it. So at long times the exponential wins when alpha is negative, but at short times it grows like t to the j. That's why this looks a lot different from this case, this case, the simple case, this one. This one, if alpha is negative, the exponential just dies. Here, if I have t to the n, t to a power, then it initially goes up and then goes down. So let's just make a little figure here. Versus t, it just goes down. This is e to the alpha t, for alpha less than 0. Or it can go up if alpha is greater than 0. How about over here? Over here, each of these terms can start out going up, but then come down. So eventually the exponential wins. Here's where j is equal to 2. If j is equal to 3, then it can start going up like a quadratic, but then eventually it comes down. So this is versus t. So at short times this is quite different from that, but at long times they're the same. What's happening here? I still have the e to the alpha t term that I had before. I had an e to the alpha t. I had it here, and I had it here. However, now it's multiplied by sines and cosines. So what happens there? Well, if alpha is non-zero, not equal to 0, and I have e to, and I'm plotting f of t versus t. Let's say alpha is negative. If alpha is negative, we break the chalk. If alpha is negative, then we would have expected, if I didn't have an omega, it would have just looked like this. But if I have a non-zero omega, then what's going to happen is it's going to look like this. It's going to oscillate in decay. The decay, and the dashed lines, I have the outline, and we know that sines and cosines have magnitude 1, so I'm going to get an oscillation here. On the other hand, if alpha is great, f of t versus t, if alpha is greater than 0, then what is going to happen? I'm going to have an oscillation as it grows. It's growing exponentially, it's growing and oscillating. And there's another case, f of t versus t, when alpha is 0. When alpha is 0, It just oscillates. Neither grows nor decays. So I can have a persistent oscillation.
So for the bottom line here, you have negative B sine omega, whatever. The B there is positive, so where's the?
Yeah, but I have an I times an I.
Oh.
It's okay. Okay, so notice how much more interesting this is than that. I can have oscillations with growth, oscillations with shrinkage, and oscillations with no growth or shrinkage. What happens when alpha is 0 here? When alpha is 0 here, I just get a term that's a constant. I just get the coefficient. What happens when alpha is 0 here? This can get really interesting, this one. This is my phone. Who is calling? Okay. So this can get interesting. When alpha is 0, if 0 is a simple root, then I just get a constant. And this is the steady state value, if I have a steady state. What happens if I have a double root? Alpha is a double root. If alpha is a double root, that says that I get, so here I have, let's say, m tilde of s over s minus 0 squared. So it's a double root. So that means I'm going to have a term that looks like t e to the 0t, and another term with a coefficient, and another term with a coefficient times just e to the 0t. Because notice I go, so I've when j is 1, then t to the j plus 1 is 0, but when j is 2, because n, so in that case I'm going to have, when j is n plus 1, well, okay, I can have j is equal to, let's get that right. Yeah, so when n is 1, yeah, when j is equal to, okay, right, so n plus 1 in this case is 2. Because I'm looking at a situation where, and let's look at this case. Here I have s minus 0 squared. So that tells me n plus 1 is equal to 2 when I compare this. So it says the highest value here is n plus 1 can equal to 2. J can equal to 2. When j is 2, 2 minus 1 is 1. So I've got t to the first e to the alpha t. So that's equal to this. Okay, so what does this look like? What this looks like, if I had, yeah, so if I had m tilde of s over s minus 0 to the first power, then I know I would just get something times e to the 0t, which is equal to 1, which is just the coefficient, a constant. On the other hand, this one, I have the constant, this is just a constant, and this is t e to the 0t. So this thing grows linearly with time. This is so I just get f of t versus t. So let's compare the different behaviors. If I have non-zero exponential, if I have alpha's non-zero, if alpha's non-zero, then I either get exponential increase or exponential decrease. And the solution is a sum of terms. So some of them may increase exponentially, some of them may decrease exponentially, and some of them might be a constant. If I have a situation with only negative alphas and 1, 0, then all the negative ones decrease, and at long times I'm just left with a constant from this case. And that's the stable case that we're usually interested in, where this is the steady state. On the other hand, if I have even, so that's stable. If I have even one alpha, let's say I have 20 alphas, but if even one of them is positive, then the system is unstable and it goes to infinity. What about here? When I have some roots that are multiple roots, then if all the alphas are negative, then even though along the way they might go up and come down, at long time they all go to 0. And if one of them is a constant, and that one happens to be a simple root, then I just go to my steady state. And by the way, we had this situation when we looked at the two CSTRs in series where T1 was equal to T2. If you remember, when we solved it using the method of ODEs, we found that we got a term that looked like T e to the 0t and T e to the alpha t, and we said that was the resonance case. That was analogous to resonance. Finally, when we have complex roots, so when roots can be complex, here you have complex roots, what we find is we get, in addition to the e to the alpha t, multiplied by the e to the alpha t, where things can either grow, shrink, or stay flat, that's multiplied by something that's oscillating. So you can oscillate and shrink when the alpha is negative, you can oscillate and grow when alpha is positive, and you can oscillate with neither shrink nor grow when alpha is 0. And what's stable and what's unstable? This is clearly unstable. Unstable. This is clearly stable. It oscillates and decays, but it decays. This one depends on my definition of what stable is. It doesn't go to 0, but it doesn't blow up. So you might call this neutrally stable. We live in a neutrally stable world. Every morning the sun comes up, and every evening it goes down and it oscillates, but it doesn't blow up and it doesn't decay. People have cycles, biological cycles, that are stable. The menstrual cycle is a stable cycle. So oscillations aren't necessarily bad or good. It depends on the situation. It depends if they grow or they shrink. This situation where all the alphas are negative is stable. This situation where even one of them is positive is unstable. This situation is an interesting one because whereas when alpha is positive, things blow up exponentially when one of the alphas is positive. Here, if I have a multiple 0 root, it will blow up, but much slower. It'll blow up linearly and not exponentially. So a multiple 0 root is unstable, but it's not nearly as radically unstable as one where I have an alpha positive. Okay, so I could have done a lot more algebra there, but I want to spend a fair amount of time there on giving you a sense of what these things mean. Now, there's some, when you have oscillations, this is often called, oscillation and shrinkage is often underdamped. I don't know why, it's just underdamped. When you have just decay and no oscillation, this one is called overdamped. That's called overdamped. What else would we like to say about this? Yeah. So let's look for a second at this particular case. If we look at this case where what are the roots here? Notice that, and I need a little more blackboard space. So example is the two CSTRs in series. Okay, so if you just copy from there, we have that CA2 prime tilde is equal to KP2 over 1 plus ST1, 1 plus ST2. And if I have a step function, CA in prime tilde is 1 over S. So I could write that CA in prime And here I have s minus 0. I'll be pedantic and write s as s minus 0. So what are my three roots here? This is a cubic, and this is first step. And then my roots are s is equal to minus 1 over t1, minus 1 over t2, and 0. So in this case, where t1 is different from t2, I have three roots, 2 negative and real, and 1 0. That's exactly this case. 2 of them are negative and real, they decay exponentially. 1 of them is 0, it's just flat. So in this case, it can also just be flat. This is alpha equals 0. And that's the steady state value. The s equals 0 gives me the steady state value. On the other hand, if t1 equals, this is not equal to t2. If t1 equals t2, then I have s is equal to 1 over t1, 1 over t1, 0. So this is a repeated root. So I'm in this situation. When I'm in the repeated root, but it's not the 0 that's repeated. So this is a repeated root. So that means I have a situation that looks like this. J is equal to 2. I have a t e to the alpha t, where alpha is minus 1 over t1. So little t e to the minus little t over big T1. Initially it starts going up linearly, but eventually the exponential wins. So this one is stable because I only have, because my zero root is the only root I have here. The only zero root. I only have one zero root. If I had 2 zero roots, I would be in here. Question is, how would I get 2 zero roots? And we can think about that. Well, how would we get 2 zero roots? Well, if one reactor were infinitely large, but we're not going to think about that case. Okay, so we'll continue with this a week from today, but a week from yesterday, next Monday is Columbus Day. Columbus Day is a school holiday. So there's no class next Monday, but next Tuesday will be a Monday schedule. So if next Tuesday is a Monday schedule, we're going to have an exam next Tuesday. Hopefully we will have our room back. Otherwise, if not, I'll have to tell you a room earlier. Hopefully by Friday we'll know if we have the room. Now, the exam will have, as I wrote on Blackboard, the exam will have 3 questions. And obviously the time for the exam is initially set to be the class time. But I don't like when people are stressed for time. I'd rather have you be able to do what you know rather than worry about time. So I'm willing to come 45 minutes early so that you have 2 hours instead of an hour and 15 minutes, but only if everyone agrees. If someone says they have a class beforehand, then I can't do it. Is there anyone who, can everyone make, instead of 11, 10:15?
Yeah.
Okay, so we'll start at 10:15. Now what are you allowed? I wrote this again on Blackboard. You're allowed to bring your text, no electronic devices, no calculators, no computers, no phones. If I see a phone, you lose the test. No phones. They have to be in a sealed bag. You obviously don't have to throw it away. It should be in your backpack, sealed, not on your desk. Then you're allowed to bring your textbook if you have a hard copy. If you don't have a hard copy, print out whatever you need and put it in a binder like this, or bound, no loose papers. And you could have your class notes, but nothing else. No homework solutions, nothing from the internet, no other solutions, just your class notes, bound. Obviously better than this, since my binding, the holes seem to have gotten too big. So bound. You could also, for example, have a page or two where you summarize your notes. That's okay in there. Just make sure it's bound. Bound means I can pick it up and shake it and nothing falls out. So obviously, if you try to staple together, that's not bound. If you try to paper clip it together, that's not bound. Bound is bound. Okay? Is that clear? Getting back to this, are there any questions on today's lecture?
Can you repeat for those two diagrams, for J equals 2 and J equals 3, what's the difference between those diagrams?
These two.
Yes.
Well, when J is equal to 2, then remember, that means n plus 1 is 2, and n plus 1 is 2, because the denominator is 2. So when J is 2, the biggest value of J is 2, then the biggest value of T is 1. J minus 1. So I have an exponential, say alpha is negative, times T to the first power. When T is small, this is pretty close to 1. So it just looks like T, looks linear. It starts out linear, and eventually it starts curving as the exponential gets big, an exponential width. On the other hand, when n plus 1 is 3, then the maximum value of J is 3 minus 1 is 2. So that says that for small times where this looks like a constant, when t is close to 0, the t squared dominates, so it looks quadratic. And then eventually the exponential wins. Now, I'm simplifying because you have more than one term. You'll have a linear term and a quadratic term. But you will have curvature then. Whereas here you don't have curvature initially.
Thank you.
Is that a really important distinction? Not the most important in the world, but it is a distinction that I wanted to make.
Thank you.
Other questions? Okay, so now you can take the pictures, the good pictures. You have all 3 boards?
I do.
I do have office hours tomorrow if you have questions.